Hi folks, welcome to a video about the area between curves, and we're going to be using integrals, which is a hugely powerful tool now, right, that we have to find exact areas between curves, right? So it's no longer about just triangles and rectangles and things with straight sides or maybe at most a circle. Now we can find the area captured between any two functions f and g. The first thing you want to remember is that that area will always be a positive number. So let's just think for a minute, though, before we jump into this lesson about the accumulator function that we just have learned about recently. So if I have, for example, a graph of f that looks like this, and I said the accumulator or area function or antiderivative is integral from 4 to x of f of t dt, then if I took a number out here, since I'm starting my area calculation at 4, the integral, this accumulator integral starts at 4, I would get g of 6 to be a positive number, right? But if I were trying to find the g of 1, right, then I would be doing integral from 4 to 1, and we learned that this would come out, this is on top of the x-axis, but since I'm going backward, this would come out to be a negative number, right? And we had all these different situations with that. We had to keep track of the signs, right? Notice that this is an area function. It's the antiderivative, and it can yield a positive or a negative answer. However, in this lesson, what we're talking about is the area of regions captured between two functions f and g. So to give you an example, it's, if you have a continuous function f and you have another continuous function g, and if you are looking then for the area captured between a and b, that would be area that looks like this yellow region. And so this always needs to be a positive number, okay? So keep that in mind as you do these problems. If you're asked for the area captured between two functions f and g, it will be a positive number. For continuous functions f and g on an interval a, b, the area bounded by the graphs of f and g and the lines x is equal to a and x is equal to b is equal to this formula, right? The area is equal to the integral from a to b of f minus g, and we're throwing in absolute value here, dx, right? And what that is all about is, because I want a positive answer, I have to make sure that I'm always integrating the higher function minus the lower function. So I've actually written that in this way on the next line. The integral from a to b, y high, which is now going to refer to the higher function, the function that has the higher y value, and then y low is going to refer to the function that has a lower y value at any specific x value, right? So we want to do y high minus y low dx. That's going to sometimes mean we have to break up our integral to make sure that the higher function is always first in this integrand, okay? When you have the absolute value, that takes care of it, right? But we are going to see different cases of how to make sure that our area answer is always positive. Let's take a look at the first example. The first example says, find the area under the line y is equal to x plus 2, so under this line, above the parabola y is equal to x squared, and between the y-axis and x is equal to 1. So in this case, we're given 4 boundaries. Let's make a quick sketch. When you make a quick sketch, you don't want to spend a lot of time putting all the tick marks in, right? You just want to just have the most important features of the graph. So if we have y is equal to x plus 2, then we know that this is an intercept 2 and slope 1 line, right? So we can just quickly draw the line like that. The other graph is the parabola, y is equal to x squared. So for that one, we can draw a few points. 1 goes to 1, and 2 goes up here to 4. So I'd have a point 2, 4, and then I'd have my parabola, and on the other side, I'd have the same thing. Okay, So there is a quick sketch of my two graphs. And then we're going between the y-axis. So the y-axis means the line x is equal to 0 and x is equal to 1. So my two vertical boundaries are there and there. Oops, that wasn't very much where I wanted to be. Let me be more precise. Okay, this is x is equal to 1. This is x is equal to 0. So remember, we want the area that's between these graphs, right? So let me actually go like this, right? That's a y high and this is a y low. And then I want to be capturing this area and we're going to write our integral for that. Okay, so that's the area I'm trying to calculate. The parabola being a curve, right? The only way we have for doing this is our integral. We can't just do it like a rhombus or something like that, right? It's a curve on the bottom. So the integral from a to b, which would be 0 to 1 of y high, which is x plus 2, minus the y low, which is x squared, dx is going to give us our answer. I'm going to be writing these integrals with a few extra parentheses when I first set them up in order to show you the structure, right? Y high minus y low and all of that. Before you integrate, though, you always want to clean up your integrand. You want to be finding the antiderivative of the simplest possible thing, right? So we're going to drop the parentheses in this case and get x plus 2 minus x squared. And then we're even going to look at that and go, is there anything, any combining of like terms or anything that I can do? There's not on this one. So now I'm ready to find the antiderivative, and that will be x squared over 2 plus 2x minus x cubed over 3. I have found my antiderivative, right? This right here, don't forget, means find the antiderivative. Once you found it, you drop the integral sign, you put the bracket on, and now we're going from the top to the bottom. Okay, then we put our numbers in. So make sure you're putting the top number in a parentheses. So 1/2 plus 2 minus a third. And then subtracting the bottom number in parentheses, which you should always check. In this case, it comes out to be 0. But sometimes, even though this limit is 0, this piece may not be 0. So always check that carefully. This answer comes out to be 1/2 plus 2 minus a third. That's like saying 3 over 6 plus 12 over 6 minus 2 over 6, and so we get 13 over 6 as our final answer. Okay, and it is a positive number as we expected. Okay, our next problem is finding the area bounded above by the curve e to the x, below by the graph y is equal to x, and between the lines x equals 0 and x equals 1. Again, quick sketch. E to the x, remember, don't waste time making tick marks. We're just making a graph that looks like that. If you want to be a little more precise, you can say when x is equal to 1, I should be up around e there, okay? And there we have a graph, okay? That's e to the x. Y is equal to x, well, that's the line that goes through the origin with slope 1, so there's the line. And we are between the two vertical lines, x is equal to 0 and x is equal to 1. Okay, so I am looking now for this area, and I will just set my integral up. I can see that for the whole stretch over which I want the area, over this whole x stretch, I have one curve, which is the e to the x curve, above e to the x curve, sorry, is here, and that's above the line, right, for the entire stretch. The curves are not changing position. The e to the x is always above the line. So this is a very simple integral. It will just be integral from 0 to 1 of e to the x, that's my y high, minus parentheses for the, well, actually we don't need parentheses here because this only has one term. But if it had more than one term, make sure you put parentheses. So we're doing e to the x minus x dx. This is y high. This right here is y low. So then we're taking an antiderivative, e to the x minus x squared over 2, going from 0 to 1. So that's e minus 1/2 minus e to the 0 minus 0 e to the 0 is equal to 1, so our final answer is e minus 3/2. Okay, let's take a look at our next problem. Our next problem says find the area of the graph, bounded by the graph of x squared minus 4, the x-axis, and the lines x equals 0 and x equals 5. So let's sketch this out. Again, a really quick sketch. Let me think about this parabola. This is a parabola, parent x is x squared, and I'm shifted down by 4. And I need to have a sketch of it going from x is equal to 0, which is here, to x is equal to 5. 1, 2, 3, 4, 5. Okay? So since when x is equal to 5, my parabola will be at 25 minus 4, which is 21. I'm just going to use a scale of 5 units per tick for the y-axis so that I can actually draw this in a realistic way, something like that. Again, the sketch is just to get us a rough idea. So I will have a graph that looks like a parabola, first of all, and it will look something like that, right? I'm making it cross here at 2 because I know that the x-intercept of this parabola will be equal to 2 and minus 2. And then in terms of the other line, it is just the x-axis, right? This is my g, or my other function. So this is my other function. And that has an equation. The equation of that is y is equal to 0. Okay, so we've got our two y's, and notice that I can't just say one of these is higher than the other for the whole interval 0 to 5. We have what I call a flip-flopping situation, right? We have a flip-flop going on right there. One curve goes under the other one while it was over before, right? They flip-flop positions. So the way we find where the flip-flopping happens is, in general, to just set the two curves equal and solve that equation. So if I said x squared minus 4 is equal to 0, right? My second curve is y is equal to 0. If I set those two equal and solve, then I will get my answer, right? In this case, it happened to be also the x-intercept because the second curve is the x-axis. But in general, this is how you find the intersection points, right? Set f equal to g to find the intersection points. Once you've found the intersection points, you know which curve is higher for each section of the integral, and now you can split the integral into two. So really what we have to write is two integrals. The integral from 0 to 2 of the y high for that stretch is 0 minus the y low for that stretch is the parabola. So that will be my first integral, and it's all dx, plus a second integral from 2 to 5, and for that stretch I have x squared minus 4 as my y high, and my y low is 0, and again it's just dx. And now I would have to just, again, please clean up the integrand. Don't be doing an antiderivative with your integrand looking unnecessarily complicated like that. The reason I'm writing it like that at first is simply to show you the structure, like how did I get this integral? I did y high minus y low. How did I get this integral here? I did y high minus y low. I'm writing it like that, and you should as well write it first like that so that you set up the area integral correctly. But then before you find the antiderivative, please clean up the integrand. So now we have the second one just looking like this. And now we find the antiderivative. Once you find the antiderivative, please drop the integral sign. And we're doing this, putting in the top number in parentheses, always checking the bottom number, even if it's 0 limit, even if the limit is 0. And then we are now at this step. Okay, now at this step, you know, you may be tempted to just like simplify this piece and then simplify this piece and so on. I find it useful to just kind of open up all the parentheses and see what may be easy to cancel or simplify after you do that, right? Make sure you distribute that negative sign. And now if you notice, the thing has a lot of symmetry at this point. Here you have a negative 8/3 and another one, so those can become negative 16/3. Here you have an 8 and an 8, so that can become plus 16. Here you have negative 20. Actually, I should have just done that as well. 8 plus 8 minus 20, that is negative 4. So we've done that. And then we only have this 125/3 left, right? So now you can combine the 125 and the minus 16 to give you, what would that be? 109/3 minus 4. And now we just do common denominator to get our answer, which is 97/3. And that is a positive number, as we would expect for an area problem. Okay, let's do another example where we are given no left and right boundaries now, and the curves are flip-flopping. So we're finding the area of the region bounded by the parabola and the line. So it's similar, or actually the same as our example number 1. So quick sketch, line, parabola, okay, and we are integrating. Oh, we don't know where we're integrating because it will just say something like find the area of the region bounded by, right? So this means the region caught in between or captured by the two curves, okay? In this case, the two curves are not flip-flopping, so maybe it's a little easier to see, but this is our region that's captured in between those two curves. So just like in the last problem, we do need to first be clear on the intersection points, right? And for the intersection points, you simply set the first curve, let's call that f, to equal to the second curve, let's call that g. So x squared is equal to x plus 1, or x plus 2, I'm sorry. And now we're going to solve that. Now, when you're solving these equations, this one gets solved as a quadratic equation. So at this stage, at this step, when you set the two equations equal, you're going to know how to have to know how to solve a variety of equations. So let's do this one by factoring. And we get x equals 2 and x equals negative 1. And what does that mean? That means that these two curves are intersecting there at x equals 2 and there at x equals negative 1. Those are the two places where the y values are equal. Here, both of the y values on the line and on the parabola are 4. And at negative 1, both of the y values are equal to 1. Okay, so we've got our intersection points, and that allows us now in step 2 to set up the integral. The integral will be negative 1 to 2 of the line, because it's higher, right? The line is our y high, minus the parabola. And the parabola is y low. And how do I know that? I know that by looking at this picture and seeing that this line is always higher or above this parabola, okay? So then I just have to go ahead and do the integral. Again, set it up with the parentheses, clean up the integrand before you integrate. And let's continue here. It's similar. The antiderivative is the same as in example 1, but my limits are going to be different. Okay, we're doing exactly the same thing now in terms of the mechanics of our integral. Okay, so now I have 2 plus 4 minus 8/3 minus negative 1, the quantity squared is positive 1, 1/2 minus 2, negative 1, the quantity cubed is negative 1, and then we've got this minus here, which makes it positive 1. So that's what I have. So now I can say 6 minus 8/3 minus negative 3/2 plus 1/3. And this is where I would first just open up my parentheses, get 6 plus 3 halves minus 8 thirds minus a third, and that would make 15 halves minus 9 over 3, which is 15 halves minus 3, which is 9 halves. And that's my final answer for that area. Notice it is a positive number again. Okay, let's do one more where we have a flip-flopping of curves. And this one says, find the area enclosed by the parabola sine. Why does it say parabolas? These are not parabolas. By the functions, I'm sorry, the functions sine x and cosine x. And we're going from 0 to pi over 2. So we are given x boundaries here. So let's make a quick sketch of the graphs. So we've got sine and cosine. We know what those graphs look like. So if I have pi over 2 and pi, then my sine graph is 0 for 0, and it goes to 1 at pi over 2 and back to 0 at pi. So my sine graph looks something like that. Okay. And my cosine graph is going to look like starting at 1 and then going down to 0 at pi over 2, and then it's going to negative 1 at pi. So the cosine graph's going to do something like that. Okay, so that's not a very good graph, is it? It's something like this. Okay, so there I have my sine and my cosine graphs, and we're asked to find the area from x is equal to 0 to x is equal to pi over 2. So that's this area that's captured in here. Remember, we're finding the area enclosed by the two graphs. So that would mean this area here and this area here. And you can see it's actually pretty symmetric. And there are some clever ways we can do this problem, but I'll just do it in the straightforward way, which is integrating, yes, from, we need to do one integral from the 0 to this intersection point, x value, and then from there to the end. So let's find the intersection, which is always found by setting the two functions equal and solving. So we're looking for where is sine of x equal to cosine x in the first quadrant. Notice that pi over 2 is 90 degrees, right? So all of this action is happening in the first quadrant. So we know that that answer is pi over 4. If you forgot that, you might solve it by doing tan x, right? Divide both sides by cosine x to get tan x equals 1, and that happens at pi over 4 as well. So the intersection is happening at pi over 4. That's step 1. Step 2 is recognizing that for the first stretch, the red graph, which is cosine, is higher than the black graph, which is sine. So my y high is the cosine, and I would integrate from 0 to pi over 4 cosine x minus sine x. And once I'm past pi over 4, that's where they flip-flop. So then from pi over 4 to pi over 2, I will integrate sine x minus cosine x. Okay? And now I have to do this integral carefully. Let's just remember the ladder. The derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of negative sine is negative cosine. And the derivative of negative cosine is sine, right? So if you write a few of these down, then you can see that the antiderivative of cosine is sine, antiderivative sine is negative cosine, etc., right? So this can be quite helpful to just write the ladder before you jump in here. So now we have sine x, which is the antiderivative of cosine x. The AD, or antiderivative of negative sine, is, here's my negative sign, right? That's positive cosine, and I'm going from 0 to pi over 4, plus AD of sine is negative cosine. So it's, this plus and minus you can combine, or I would just leave it like this for now. We'll combine it later. The AD of negative cosine is negative sine. And then we're going from pi over 4 to pi over 2. So we got kind of two pieces of action going on here. So let's do the first. Sine of pi over 4 rad 2 over 2 plus cosine of pi over 4 rad 2 over 2 minus, careful here, sine of 0, 0 plus cosine of 0, 1, right? So that is all of this. This is all of this, okay? And now I have to do the second part, and that's a plus. And then I'm going to do all of this. Use a different color here, all of this, okay? So negative cosine of pi over 2 is negative 0. Negative sine of pi over 2 is negative 1 minus negative cosine of pi over 4 minus sine of pi over 4. Okay, so this is all that I have here. And this blue goes with the blue and the gray goes with the gray. So now cleaning it all up, it just becomes rad 2 over 2 plus another rad 2 over 2 makes rad 2 minus 1 plus, this is still a minus, right? So it's actually going to be minus another 1. And then here, these two are going to combine to be negative rad 2, but then this negative will turn it into positive rad 2. So my final answer will be 2 rad 2 minus 2. Okay, so let's just finish up here. Example 5 is on a second video, so please refer to that video for this example, and that will show you how to do all of this with a calculator. It's an important video, so please watch that. This example 5 is on another video, and that video is named Lesson 7-4 Area Part 1, Example 5. Okay, so watch that one, and let's finish up now with the takeaways. So we have our takeaways here. So true or false, if f and g are continuous, and if f is greater than g for all x in AB, then the area bounded by f and g on AB is given by the integral from a to b of f minus g. So think about that for a minute. Pause the video. So this first one is true, and the reason is that if f is greater than g, then we don't need the absolute value because this is always y high and this is y low on the stretch from A to B, okay? Our second question says the area bounded by two curves can be a positive or a negative number, and that is false. And the reason is, as we said at the very beginning of the lesson, in these type of problems, your answer always has to be a positive number. There is a second video on area, so please make sure you watch that. That is called Lesson 7-5, Area Part 2, and that's going to show you some other techniques to find area. I hope you enjoyed this lesson. Have a wonderful rest of your day.